Okay, tube timers, welcome back. We're going to enter something called the ToobTime tutorial. It's a different world, don't you know? The ToobTime tutorial series is a small series that is based on some developmental aspect of what we're looking at or what we're doing. So the first one is a tutorial on two of the most important formulas for transformers for novice audiophiles. The first important formula is the turns ratios formula, and the second is the impedance, transformer impedance formula. So let's get started with the transformer ratios formula. And it is what I like to call, or what I learned to call, the TI formula. T-I-E. And to make it a formula, we've got to have some fractions going here. So you do the same thing over again. TI. And this equals this, and this equals this. And the first is the turns. So the number of primary turns, the amount of current flowing in the secondary, and the amount of voltage across the primary. Turns of the secondary, I is the current through the primary, and E is the secondary. Now look at this. I've remembered this for, since 1973 when I learned it. And it's so easy to remember because it's a tie formula, like you wear a tie. And you start with the first letter of the tie formula, that's your primary. Secondary, primary, secondary, primary, secondary. That's all there is. So if you know the voltage of the secondary, you input it, and you read it on the primary voltage, take that equation, that fraction, and that will give you the turns ratio, N. Okay, so to start, let's draw a picture of a transformer, or a symbol anyways. So here's a transformer. Put some iron core in here. Generally, the two lines here mean an iron core transformer, where if there's nothing in there, it means it's an air core. On this transformer, we're going to have an extra tap. It's a 4 ohm tap. The transformer itself is an 8 ohm output. And here's our zero reference. Okay, this is the primary. So if this were a output transformer, we would have a tube coming down off this primary, much like as such. We'd have a tube, and it would go probably to some ground or reference, and this would be our B+. And that's how the transformer would hook up with a tube in the circuit. Now, my question is, regarding this Sunbuck amplifier, what is the impedance looking in here to the transformer? Now I know the 6P1 tubes are, I think it's 5,000 ohms for one, 5,000 ohm load for one tube. Two in parallel would require about 2,500 ohms. Now I want to show the TI formula, I want to show the impedance formula, and how we can derive that quite simply with a minimum of instruments and just a skosh of arithmetic, algebra, I guess. So, let's get started. Oh, before we get started measuring, I'm getting excited to measure. Let's get started by looking at the turns ratio TP over the turns on the secondary. That fraction is N, or the turns ratio. So if we had a primary, for example, if our primary turns were 14 and our secondary turns were 2, we'd have a turns ratio of 7. Now, if you notice up here, primary, secondary, if we can put in a voltage and measure the current, or the if we can put a primary or secondary voltage in and measure the voltage of the secondary, we will develop N. And we need N for our transformer impedance formula. So now that I've thoroughly confused you, let's watch the video to see how this develops out. Okay, so here we go with our turns ratio measurement setup. To remind you, we have a 6P1 tube amplifier by Sunbuck. Duke Audio and Noob Sound also makes a similar model. We are measuring our input voltage and output voltage. This is an AC voltage. And we are going to determine the turns ratio of our output transformers. Now, we have an 8 ohm output. These are the output connections here. The ground, 4 and 8. Ground, 4 ohm, 8 ohm. And these connections are going inside the amplifier to the primary of the output transformer. So when I put my voltage into the speaker terminals, I will measure the reflected voltage coming out on the output transformer. A little bit of glare on that, but I guess that's okay. Well, maybe we'll step it up and get a little darker. Okay, that's good. Okay, so we're in the 8 ohm output. I know that I want to get a nice strong signal into it, so we're going to emulate an 8-watt signal coming out of that transformer, and an 8-watt signal onto an 8 ohm resistor is 8 volts. How nice is that? So let's turn her up to 8 volts and see what we get for a primary voltage. I'm shooting up to 4, shooting up to darn near 6 volts. We'll creep a little higher to 7, 7.7, 8.5. It's a really coarse on this variac. It's really low in the range, and it's not a real happy camper there. All right, 7.99 volts. That's incredibly close to 8 volts. So we'll write down 7.99 volts. And we get 143.5 volts out. 143.5 volts out. Perfect. Now we're going to repeat this for the 4 ohm measurement. As I move this, I've purchased tubes from Tube Depot before, and I kind of like them. They sent me that nice sticker. I don't know what to do with it, so I thought I'd just put it here. I'm not getting any compensation from these people, but you never know. I just like their product. Okay, so now we have our. Let me turn this down a little bit. Turns out that 6.66 volts is the load that would produce 8 watts on the 4 ohm speaker, and 5.66 volts. Man, it's an afternoon. Here's pretty close. 5.7, 5.54, and I'm just dusting the knob. Okay, so 5.63 volts yields 153.2 volts out. Okay, so that's the 4 ohm load. So now we'll continue on and determine the turns ratio and the impedance of the impedance that the tube sees using the transformer calculations. So let's take a look at this and see what we get for a turns ratio. As I said earlier, box this off, recording these things off so we don't worry about the old stuff. We saw that for the 8 ohm input, 8 ohm input, well, that's kind of neat. Let's check the eraser, see how that works. And the eraser is the same size as the pencil, so it's going to be a couple of cleanings here to make it work right. Alrighty. 8 ohms. So we put in the equation is EP over ES, voltage in the primary over the voltage in the secondary, equals N, the turns ratio, because TP over TS is the turns ratio, and so that N equals either IS over IP or EP over ES. And we saw we had 143 volts out, and we had 7.99 volts in, and so that gives us a turns ratio of 17.96, and we'll just call that 18. Now, we'll do the same thing for the 4 ohm load. So we have EP over ES equals the turns ratio. And we measured 153.2 volts over an input voltage of 5.63, and equals our turns ratio. And so our turns ratio N equals, I'll use a calculator here, 153.2, 5.63 is 27.211. 21. And we'll just call that 27 for making easy multiplications. Now this is a little bit concerning because this ought to be darn close to the same. So I'm wondering a little bit what I have going on here. Okay, so what I'm going to do is create a new image. Oops, excuse me. We're going to, let's see, image. I've forgotten how. I use a couple of different programs here, and so I'm not looking. I'm looking for a new file, and it's not a new image, a new blank image. Thank you. So the turns ratio for 8 ohms equals, we called it 18, but the turns ratio for the 4 ohm input was 27. Now I know that's going to be a problem right off the bat because they should be about the same. So let's introduce our transformer impedance formula, which is the meat of what we wanted. And that is Z, the impedance of the primary. What the heck I'm doing here? I don't know what's going between brown and black. Is equal to the impedance of the secondary. And that equals the turns ratio, NP over NS squared, and that equals also conveniently V of the primary over V voltage of the secondary squared. Now I apologize for confusing E for V and T for N, but that's the way I wrote down this impedance formula, and it doesn't really make any difference. It's just nomenclature. So in reality, we figured out the VP over VS. That's what we measured. So we're going to say the Z of the primary equals the impedance, or Z of the secondary, and that's equal to V of the primary over V of the secondary squared. Now, to be sure, when you square something, that's the same thing as VP over VS times itself. VP over VS. Okay, so we showed earlier, we measured VP and VS, or EP over ES, and for the 8 ohm input we got 18, and for the 4 ohm input we got 27. So we were curious as to the impedance of the primary for this transformer. So ZP is our primary impedance over ZS, which in our case is going to be 8 ohms, because we're going to study the 8 ohm case. And that's going to be equal to the turns ratio, 18 squared. So let me just clean that up a bit, because I really wanted to put 8 ohms in here. All right, 8 ohms. Now, all we need to do is square this number, multiply it by 8, and that gives us ZP. So ZP equals to 8 times 18 squared, which is 8 times 324. That's 18 squared. Thank goodness for the calculator. 324. 8 times is 2592. So that says ZP equals 2592 ohms. Well, that seems reasonable, because the transformer should be around 2500 ohms for a 2 tubes in parallel. For an 8 ohm, for a load impedance of a single tube being 5,000 ohms. So now let's take this 4 ohm, which I can already see is going to be a problem, because those turns ratios should be the same. These should equal each other. They are not. So that's going to be a problem. So we use the same formula, the impedance of the primary over the impedance of the secondary, and that equals the primary voltage over the secondary voltage squared. Oh man, I remember when I was in university, we had to start from scratch and derive all these formulas. That was a hoot and holler. So now the primary voltage, or the primary impedance using the 4 ohm load, is equal to 27 squared. And so using the same math as we did down here, the same equation, we see ZP equals ZP equals 4 times 27 squared, and ZP equals 27 squared is 792. 4 ohms times that number is 2916 ohms. All right, you can see the problem. These should be the same reflected primary impedances. They are not. So we're 400 ohms off. Now the question is it me? Or is it this transformer? Now I suppose it's possible. There's a real cluster in there. I suppose it's possible that I did not clean up all the circuitry, but I think I did, so I don't know. This could be just a bad transformer. For your information, I was a little bit surprised by this result, so I checked the second transformer of that stereo pair, and I got similar to same results. So, let's try a different Chinese transformer. Well, okay, here we go. I really wasn't impressed with what came out of the 4 and 8 ohm taps on the 6P1. So I grabbed another Chinese transformer, and I wanted to check. This one happens to be a push-pull transformer, so I'm measuring between plate to plate. And for an input right here, I've got a kind of close frame, so it's hard to see the parts. So I'm going to inject a voltage into the 8 ohms. I put 4 volts into the 8 ohm. I'm using a signal generator this time, not my Variac setup for a little better resolution or a little control of the input. And I put about 4 volts in, and I got 110 volts out on the 8 ohm load. Now, we'll disconnect the 8 ohm and attach it to the 4 ohm lead. And the 4 ohm lead, we will also put 4 volts into it. Or maybe we won't. Guess it's too much load on the signal generator. Okay, so I'll put just 2 volts in. What do you think about that? So I put in 2 volts and I get out 70.7. 2.025. 2.025. I'm writing this down, that's why I'm saying it again. And 70.8 volts. Okay, so let's go through this and see what we get. With a new blank image, and using our TIE formula, we know that the turns ratio equals the voltage of the primary over the voltage of the secondary. And for the 8 ohm case, we get 101.3. I believe I said 110 in the video. Sorry about that. It's really 101.3. And we divide that for our input voltage of 4.089. Now, we know our turns ratio equals 101.3 and 4.089 divide, and we get a turns ratio of 24.77, and we're going to go ahead and call that 25. Now, if you recall from this is our TIE formula. If you recall from our impedance formula, we get we take our turns ratio n, so our z of the primary over the z of the secondary, that's the primary impedance over the secondary impedance, we get 25 squared. Now we know the z of the secondary in this case is 8 ohms, and so the z of the primary is equal to 8 times 25 squared, and so the impedance of the primary of that transformer appears to be sorry about that, phone call ringing. 8 times is 5,000 ohms.
Call from Lynn Mary's.
Okay. Boy, that's a nice number, isn't it? The only problem is this other Chinese transformer was a 20-watt, 6K ohm primary impedance. Huh? I don't know what that means. I don't know why this is like that when that's like that. Maybe somebody can tell me. So let's try the 4 ohm side, just for the fun of it. So on the 4 ohm side, we get the same thing, VP over VS, and that equals, in the 4 ohm side, we got 70.8 volts, 70.8 over 2.025. Okay, so remember, if you recall, I put 2 volts on the secondary of the 4 ohm tap of the transformer, and I read 70.8 volts across the plate to plate. And so that gives us 70.8, enter 2.025 divide, and we get 35. And for the 4 ohm side, we're going to now see what the primary impedance is. And that's our turns ratio for the 4 ohm side, 35. So now we get our impedance formula out. ZP, got to cross this down here. Oops, that was kind of a weird thing. Over ZS equals 35 squared, which is equal to ZP equals 4 ohms, because we're going in on the 4 ohm tap, times 35 squared. Kind of ran off the edge there. Looks like a 33, but it's a 35 squared. Don't let it fool you. 35 squared 4 times. Oh, I made some kind of mistake here. 35 squared, enter, 4 times. So if we get a primary impedance of 4,900 ohms, which is darn close. It's kind of close to the 5,000 ohms of the 8 ohm tap. 8 ohm tap. And this is the 4 ohm tap. Again, 4 ohms or 8 ohms. This Chinese transformer was a 20 watt 6K according to the documentation, and 5,000 is pretty far away from 6,000 ohms. So if I wanted to use this transformer as a 6K load, I'm thinking I'm getting 6K, but in fact it's 5K, which means I'm going to miss my optimum power transfer. Okay, so now I used 2 Chinese transformers. It did not impact, or it did not work the way I was kind of hoping it would. So now you're probably thinking, what the heck is this guy doing? So when I do this, I say, okay, let me take another transformer. I'm going to take an EdCore transformer. An EdCore is a transformer made here in the U.S. I particularly like them. They're reasonably priced, and they perform very well. So I'm going to take an EdCore transformer and make the same measurements and see if I get the same craziness. Okay, am I losing my mind or what? This is a very simple action to take. Measure the voltage into the transformer and what comes out. So I wasn't impressed with the second Chinese transformer, and so I pulled an ED core, a good old US made core, and put in down here on the output, I put in my 4 volts, and on my primary side, I get out 77.3. So we'll see what that does. I'm telling you, it makes you sort of wonder what the heck you think you know when this kind of stuff happens. If anyone has an idea as to why the Chinese transformers are behaving this way, let me know. Drop me a note in the comment, because this is very unusual. This should be a very straight and easy measurement. Oh well, I guess we'll see what we see. I want to go through the calculations on this one. Okay. So I couldn't measure the 4 ohm tap because that particular transformer didn't have a 4 ohm tap. And of course, that would be a bit of a problem. EdCore, I don't know why, they seem to always make single output transformers. You can get a 4 ohm transformer or you can get an 8 ohm transformer, but it's kind of hard to get one with 4 and 8 ohms on the output. So with our EdCore, it's a 25 watt, 3,000 3K ohm primary impedance. So if I don't get something close to 3K ohms when I run through this, I don't think you're ever going to see this video. I'm going to go back and figure out what the heck I did wrong. Okay, so we have our V primary over our V secondary equals our turns ratio N. Our V primary was 77.3 volts, 77.3. And the input voltage was 4.021. So we get a turns ratio. Okay, a little bit messy there. We get our turns ratio of 77.3 and 4.021 divide. And we get a 19.224. Okay, we'll just hang on to that whole number because we'll see what we get. So now our impedance transformation ratio says that if you recall, Z of the primary over the Z of the secondary equals the turns ratio N squared. Of course, that's N. And if we say ZP equals 8, because that's our impedance tap we've moved out on, times 19.224 squared, we get 19.224 squared, 8 times, we get 2,956 ohms. And that's darn close to the listed impedance of the transformer. So what did we learn here? Well, we learned to be a little bit suspect of our Chinese friends when we're buying their inexpensive transformers, and I will say they're inexpensive. They're the cheapest I found on AliExpress. We'll be a little bit suspect of those things, and we'll measure them for the turns ratio and impedance before we actually put them in a circuit to make sure that it's relatively close to what we want for load impedance. If we stick with a name brand Edcore, Hammond, those kind of people, we'll probably get what we pay for when we buy it. Of course, now, mind you, these transformers are going to cost 2 or 3 times what a AliExpress transformer will get you. So I suppose you get what you pay for. The equations, of course, I'm going to repeat them up here because these are very, very important. If you know this, you have got 99% of your transformer questions answered. So the first one was the TIE formula. TIE equals our TIE formula. Primary, secondary, primary, secondary, primary, secondary. There's our TIE formula for determining our turns ratios. Or, of course, you can, if you know what your turns ratio is on the transformer, and you know the secondary or the primary current, you can calculate the secondary current here. And the impedance formula, which is, and this is a very important formula used in conjunction with the above formula, ZP over ZS, the impedance of the primary divided by the impedance of the secondary. And we said that was the turns ratio squared, and we also know it's V of the voltage of the primary across the voltage of the secondary, which is our turns ratio formula we use in this case, squared. So, I hope you tube timers have learned a little bit of something from this. It's an important formula. If you have a transformer on the shelf and you know some fundamentals about it, you can determine its input impedance as far as the tube is concerned. In the next series, I'm going to talk a little bit about the next tutor series is going to talk about the maximum power transfer formula, and that gives you an idea of why you want to match your output load impedance to the one specified for the particular output vacuum tube you're using. Okay, tube timers, if you like this, please hit the thumbs up button down below. And if you have any comments or suggestions for another tutorial series, please write it right down in the comments. And of course, subscriptions are always appreciated because that helps me see what people like. Take care, everybody, and that's a wrap.